It's a pleasure for me to welcome Pedro here, who is a PhD student here at the CAB, working at the Spanish Virtual Observatory. And Pedro's just got back from a research stay at the UC San Diego, and he's focusing in his PhD on machine learning methods and how they can be applied to exploit astronomical archives. And that's sort of what he's going to talk to us today about, focusing specifically on how that can be applied to M dwarfs and ultra compact dwarfs, or ultra cool dwarfs, sorry. So with that, I'll sort of let you take it away, Pedro. So thank you very much.
Thank you, Lee, for that nice introduction. So as Lee said, I'm Pedro Mas. I'm a PhD student at the Spanish Virtual Observatory, which is this amazing team that you can see here. Although we are not the best ones are taking center photos, but we have an amazing team. And today I'm going to talk about a new line of research that we opened during the recent years, which is focused on the use of deep learning, on the study of the capability of deep learning techniques to exploit available astronomical data. Okay, and specifically today, I will focus on the use of deep learning and deep transfer learning for the study of M dwarfs and ultra cool dwarfs. So this is the outline of this talk. First, we will introduce the science that we want to investigate, that we want to research. And this includes M dwarfs, which are the cooler stars of the stellar population, and ultra cool dwarfs, with which we will go into the superstellar realm or superstellar domain. Then we will introduce the techniques that we use to do this science, which includes several techniques of deep learning and deep transfer learning, including autoencoder neural networks and convolutional neural networks. And we will see how we can use these techniques to study this kind of objects. And after this introduction of the science of data techniques, we will go into our actual work or the results that we have obtained, both in the analysis of M dwarfs and ultra cool dwarfs. So let me first introduce you to the M dwarfs, which are basically stars that are smaller, cooler, and fainter than stars like our sun, that sound like stars. Because of this, they have a very small mass range between more or less 0.1 and 0.6 solar masses, and a very low temperature range between more or less 2,300 Kelvin and 3,900 Kelvin. Okay, so they are very little, they are very cool, and they are very faint. And they are very interesting because these stars are by far the most common type of star in the solar neighborhood, vastly outnumbering other hotter types of stars. And as you can see in the figure, they are located in the lower tail of the main sequence. What we can see here is an HR diagram. In the y-axis, we have the absolute magnitude in the Gaia G band, which is in the visible wavelength range. Here, smaller values means brighter, and bigger values, higher values means fainter. And in the x-axis, we have the color between the Gaia G and Gaia red bands. Okay, so here a bigger value means cooler objects and a smaller value means hotter objects. And as you can see, we can find our M dwarfs are located in this gray area that is highlighted, which is located at the very end, at the very lower tail of the main sequence, which is this bright line that we can see in the diagram. And M dwarfs, because of their low mass, they are partially or fully convective, and this means that the fusion of hydrogen is very slow and very efficient in their interiors, and because of this can have very long lifespans that can extend to tens of years or billions of years. And they are very interesting because the stellar properties, like in comparison to other stellar types, in M dwarfs, the stellar properties change a lot, change significantly from earlier types, starting from M0, to later types, finishing with M9 M dwarfs. And the most important, or the most significant of these changes is that for masses below 0.35 solar masses, which is equivalent to a spectral type of M3 or M4, M dwarfs became fully convective. And because of this, a large fraction of cool or late M dwarfs are magnetically active. And we can see this stellar activity in phenomena like a strong chromospheric activity and frequent flare or coronal mass ejections phenomena. In the earlier stages of their life, M dwarfs are very fast rotators, rotate very rapidly, and therefore, sorry, have a very strong stellar activity. But when they reach the main sequence, they start to spin down because of the loss of angular momentum due to the stellar winds. And as they spin down, they therefore experiment a decrease in their stellar activity, sorry, over time. This is known as the spin down of M dwarfs. And here in the figure, you can see an example of this activity. Here we have two stellar spectra. In the y-axis, we have the normalized flux, and in the x-axis, we have the wavelength in angstroms. So in the top orange spectra, we can see an M5, and in the bottom red spectra, we can see an M8. Okay, and the lines that we have there identified are very strong emission lines, specifically H-alpha and the calcium 2 HK lines, which are very strong indicators of a strong chromospheric activity. Okay, but why is it important to study M dwarfs? So there are several reasons, but today we are going to focus on two of them. The first one is that because of their low mass, small size, and faintness, combined with their prevalence or abundance, their longevity, and their proximity, these M dwarfs are very suitable targets for the detection of close-in Earth-like planets orbiting around them. Okay, as they have a very small size and they are very faint, it is easier to detect planets transiting them than in other hotter types of stars. Okay, but in this field, it is very important, it is crucial to have a precise determination of the stellar parameters to correctly characterize the exoplanet that we detect. Okay, and this is a very complex topic in the M dwarfs because as they have very low temperatures, we can find there are a lot of molecular absorption bands in their spectra that make very difficult or non-trivial to estimate the stellar parameters from this spectra. Okay, we need to also characterize very good these stars because, as I told you, latent dwarfs are magnetically active, so they can be also a problem for the search of exoplanets orbiting around them, and in terms of habitability. And the other thing that we are going to explore today, and that I want to highlight today, is that M dwarfs are the last frontier before the superstellar realm, before the superstellar domain, where we can find the ultra-cool dwarfs, which are, when we talk about ultra-cool dwarfs, we are talking about objects with spectral types starting from N7 to the extended L, T, and Y. So more in detail, here you have a brief summary of ultra-cool dwarfs, and these are objects that are cooler than more or less 2,800 Kelvin, which is the temperature in which the absorption bands start to be very significant. And among the ultra-cool dwarfs, we can find latent dwarfs with a spectral type, latent dwarf stars, with spectral types of F7 and later. And then we can find superstellar objects known as brown dwarfs and planetary mass objects. And to understand the difference between these two latter ones, we have to go to the superstellar boundary, which is the limit in which hydrogen fusion can happen in the interior of a star, of a stellar structure. And this superstellar boundary is equivalent to a stellar mass of 0.072 solar masses. So beyond this superstellar boundary, we can find different types of objects. If they are massive enough to fuse deuterium, we are talking about brown dwarfs, which are not massive enough to fuse hydrogen, but massive enough to fuse deuterium. And if the object has a mass below the limit for fusion of deuterium, we are talking about planetary mass objects. Okay, and just for you to make an idea of these objects, in the most up-to-date compilation of ultra-cool dwarfs with a reliable spectroscopic characterization, we can find around 1,500 objects with a spectral type of L0 or later. And we can use these objects to build the HR diagram but this time in the near infrared, okay? So in the figure we have now, in the y-axis, the absolute magnitude in the J band, and in the x-axis, we have the color between the J and the H near infrared bands. And what we can see here is that ultra-cool dwarfs go redder and redder in the color as they go, as their spectral type goes down, until they reach the late L types. And then we can see that in the transition from L to T types, the ultra-cool dwarfs suddenly go or start to go bluer in the color. And we will go more into detail into this phenomena later in the talk. But this is because of this, in this LT transition, we have a very strong absorption because of methane in the atmosphere. And this, because of this, the flux in the H and the K bands is strongly reduced. So the color gets bluer compared to the J band. Okay, so how do we study these objects? In our research, we use two different types of data to study these objects. In the case of the M Dwarfs, we use high-resolution spectra observed with the CARMENES with a spectrograph. This is what you can see in the red plot. And for the case of ultra-cool dwarfs, we use, as they are very faint, we have to use near-infrared, low-resolution spectra. In this case, in this talk, we will talk about a spectra observed with the SPECS spectrograph, which is in the IRTF telescope. And this is what you can see in blue. And just for you to make an idea of the difference, in the high-resolution spectra, we are seeing a wavelength window of 35 angstroms. And in the blue spectra, we are seeing a wavelength window of 7,000 angstroms. Okay, so they are very, very different type of data. And now let me introduce briefly the techniques that we use to study these objects from the data that I just introduced. And what you have in this slide is the three main terms of the AI paradigm, of the artificial intelligence paradigm. So first we have artificial intelligence, which is a field that studies the machines that mimic human intelligence to solve problems. Then we have machine learning, which is a subset of artificial intelligence in which systems automatically learn from the data and make predictions in new data without rules, without being explicitly programmed to. And then we have deep learning, which is a subset of machine learning in which multi-layer neural networks automatically extract features from the data and learn or create a hierarchical representation of the data. And this is the big difference between machine learning and deep learning, is the extraction of features. In machine learning, this is performed or done by the user. And in deep learning, this feature engineering, as we know it, is performed automatically by the neural networks. So deep learning methodologies are, of course, very promising, but they have two major constraints when it comes to data dependence. One is that the training of these systems, of these processes, is very expensive in terms of both time and resources, and that the training of these systems rely on massive, the big, huge training data sets. And as you know, in science, it is often very complicated to create or obtain a bigger enough label training data set, and it is often impossible. And this is why synthetic data is often used to train these models. But this can be a problem if the synthetic data that you are using to train the models is not identical to the real data that you are going to infer into. And this is what we know as synthetic cap, which is just the difference in feature distributions between the synthetic and the observed data. And here you can see an example in the figure. This is a wavelength section of one of these high-resolution spectra that we are using in our research. The solid line is the real observed spectrum, and the dashed line is the synthetic spectrum. As you can see, they are very, very similar. They are very close, but they are not identical in some features. And this is where transfer learning comes to help because it can reduce these two major constraints of deep learning. Here you have several definitions of deep transfer learning in this slide. But basically in transfer learning, we always have a source domain and a source task, and a target domain and target task. And the idea is that transfer learning enables us to enhance the performance of a predictive function in our target domain using the knowledge available in the source domain. And we talk about deep transfer learning when this predictive function is indeed a neural network. Okay. So basically the idea is that transfer learning allows knowledge to be transferred from a source domain to a related, but this is important, not identical target domain. And this can be very complex or very difficult to understand at the start, but there's a very easy way to see it, and it is that it is easier to learn how to ride a motorbike for a brain that already knows how to ride a bike than for a brain that doesn't know how to ride a bike, okay? Because we take the knowledge that we acquired in one domain and we transfer it to another one to improve a task in another one, okay? And the way a deep transfer learning procedure is usually done is that a deep learning model is pre-trained in a data-rich domain, and then the knowledge acquired in this data-rich domain is used to improve the generalization in our data pool target setting, which is the one that we are going to infer, or we are going to do science with. And just to locate our work with this deep transfer learning procedure is part of a new line of research within the CARMENES consortium that was open to study the capability of deep learning to determine stellar parameters from high-resolution spectra. Okay? And our paper is the third of a series of papers. The first one is Passage et al. 2020. This was the first one, where they used a convolutional neural network directly on the stellar spectra to determine stellar parameters from CARMENES and dwarfs. You can see this model inside the blue box, where you can see first the convolutional layers of the network that extracts features inside a feature vector, and this feature vector is fed to an artificial neural network block to estimate the stellar parameter. So in this work, they achieved very promising results, but they found significant deviations in the metallicity estimations that they attributed to the synthetic gap. After this work, the second that we have is Pedro Garcia et al. 2023, where they developed the first deep transfer learning approach in order to solve these deviations found in the previous work. And what they can see, as you can see in the red box, what they did is to take the feature vector extracted by the convolutional neural networks of Passage et al. 2020, but they trained again the last block of the network, the artificial neural network block, and they train it again with high quality stellar parameters measurements. And they achieve good results again, but they had a very big constraint, and it's that they lack a sufficiently big or sufficiently large number of reference stars to do this transference of knowledge. And then after these two works comes ours, and this is the big picture of our work with M Dwarfs in CARMENES. So the main idea of our work is to develop a deep transfer learning approach based on autoencoder neural networks that I will now introduce to determine stellar parameters from high-resolution spectra. Okay, and for this we have a target domain, which is a sample of 286 high-resolution spectra from CARMENES of M Dwarfs, and a source domain, which is a data-rich grid of synthetic spectra that is based on the Phoenix ASUS models. And the expectation with this work is to bridge the synthetic gap, and that is to reduce the differences between the synthetic and the observed data that we use as input for the stellar parameter determination. And this synthetic gap is what you can see in the figure. Here you have a two-dimensional projection with a technique called UMAP of all our data. The dots color-coded by temperature is the grid of synthetic spectra. And the dots, the gray triangles that you can see isolated are the real CARMENES spectra. So as you can see, most of this observed data is isolated, is totally isolated from the grid of synthetic data. So this is not good because that means that they are not identical. So we want to solve that, and the first step in the methodology to solve that is to use autoencoder neural networks to obtain low-dimensional representations of the synthetic spectra. And here in the slide, you can see a diagram of one of these autoencoders, which are neural networks that are composed of two blocks. One is the encoder neural network that takes the input data and brings it to a low-dimensional representation, which is known as the bottleneck or latent space. And then we have a decoder neural network that takes this low-dimensional representation and tries to reconstruct the input data. Okay, so the rationale behind this kind of neural networks is that narrowing the flow of information and minimizing a reconstruction loss between the reconstructed and the original data, we force the autoencoder to automatically learn a meaningful low-dimensional representation of our data. So the first step in our methodology is to use these architectures to obtain low-dimensional representations of our synthetic spectrum. And just for you to see how it looks like, here you have two figures. In the first one, you have one example of this synthetic spectrum. In blue, you can see the original one. In red, you can see the reconstruction. And you can see that they mainly overlap because they are nearly identical, as you can see in the residual plot below. But what is interesting is the second figure, that is the actual latent low-dimensional representation, in this case, 32 dimensions. For you to make an idea, the input dimensions are 3,501, so we reduce them to 32 dimensions. And this is the latent space, the low-dimensional representation that is learned by the autoencoder. Okay, this is actually a 32-dimensional vector. It has been reshaped to a matrix just for the visualization. And this is just for you to see that achieving a good reconstruction with an autoencoder is the result of a high number of iterations, and you have to search for the optimal hyperparameters of the neural network to achieve a very good representation of the data. Once you achieve a very good reconstruction with autoencoder, that means that you can use this low-dimensional representation instead of the original data. So you can see how at the start of our work, we were not achieving very pretty reconstructions. Okay, so with these autoencoders, we obtain the low-dimensional representations of the synthetic data, and then we introduce the deep transfer learning step with the objective of transferring the knowledge from our data-rich source domain, the synthetic grid of spectra, to our data-poor target domain, which is our sample of CARMENES spectra. And for this, we use an approach which is known as fine-tuning, in which the autoencoder network is retrained, is trained again with the real CARMENES spectra, but this time we keep all the encoder layers until the last one frozen. And by frozen, I mean that they are not updated in this retraining. Okay, we only leave free the last part of the encoder. And why do we do this? Because as I said at the start, the neural networks are hierarchical. So what we want to do is to preserve the genetic learning from the source domain, which is stored in the lower layers of the trained autoencoder networks, which are the layers closer to the input. But we want to tailor the specific features, which is stored in the higher layers, the largest layers. We want to tailor these specific features from the target to the target spectrum. Okay, we want to preserve the genetic learning of the data-rich source domain, but tailor the specific features to our target domain. And this is for you to see the importance of this step. Here you can see two examples of reconstructions for a real CARMENES spectrum. In the top, we can see the reconstruction with no deep transfer learning before the transference of knowledge. And in the bottom, we can see the reconstruction after this transference of knowledge. So you can see how the reconstruction is much more better, accurate after this transference of knowledge. Okay, you can see this in more detail here. Here we have a wavelength section for one of these real spectrum. In blue, we have the original CARMENES spectrum. In red, we have the reconstruction before the deep transfer learning. And in black, we can see the reconstruction after this transference of knowledge. So you can see how by adding this deep transfer learning step, the autoencoder learns to preserve much more specific features from the input spectrum. Okay. So with the initial training of the autoencoders, we obtain low-dimensional representations of the synthetic spectra. With the deep transfer learning process, we obtain low-dimensional representations of the CARMENES spectra. And with this, we build a new feature space in which no significant difference between the synthetic and the observed data are observed. And this is what you can see in this plot, which is the same two-dimensional UMAP representation, UMAP projection, but this time using the low-dimensional representations that we found in our methodology. And now you can see how these CARMENES dots, how these CARMENES points are much more integrated along the grid of synthetic data than before. So the last step in our methodology is to use this new low-dimensional feature space as input for a one-dimensional convolutional neural network. That is the one that finally estimates the stellar parameters. And here you can see a diagram of this neural network. First, we have, again, the convolutional layers that explores the input vector and extracts new features in a feature vector that is used by the last block, by the artificial neural network block. This block uses as input the feature vector to finally estimate the stellar parameter. And for this, like using this, what we do is to train this convolutional neural network with the low-dimensional representations of our synthetic spectra and use the trained network in the low-dimensional CARMENES representations to obtain the stellar parameters. Okay, and just for you to know that if you are curious to see all the code used to develop and train these networks, it is available to everyone in GitHub. And with this methodology, using this, these are the results that we obtain. What we can see here is the same diagram that summarizes the predictions of the stellar parameters that we find. In the y-axis, we have the volumetric luminosity. In the x-axis, we have our estimated effective temperatures, which is reversed along the axis. The color of the dots is our predicted metallicity, and the size of the dots is our projected rotational velocity. Okay, so what the important things that we can see here is that most of the overluminous objects that we find above the main sequence are indeed active objects, which are the triangles in the first plot, and most of these are also young objects or kinematically young objects, as we can see with the circles and the crosses in the second plot. Okay. We also can see the gradient of metallicity along the main sequence with the color, and we can see also in the first plot that nearly all the very low metallicity objects that we find are actually kinematically old for the thick disk population. And to compare our results with the previous works that I just mentioned, this is the comparison that I mentioned at the start of the talk, sorry. This is the comparison with the results from Passeggier et al. 2020. In the x-axis, we have our estimations. In the y-axis, we have the estimations from the literature. First, we have the comparison for the effective temperature. In the middle, we have for the surface gravity, and the third one is for the metallicity. And what we can see is that we achieve very good consistency with the results for Passeggier et al. 2020, as expected, but we managed to correct the deviations that they found in the metallicity and that they attributed to the synthetic gap. So we can see how using a deep transfer learning approach, we are able to correct these deviations that they found in the metallicity. You can see this in the last plot. And this is the comparison with the results from Bello Garcia et al. 2023. We cannot see here the surface gravity because they didn't estimate it. And we can see one thing here, and is that as they used a very small number of reference stars for the transference of knowledge, they found that the results of effective temperature were very tailored to this very few number of stars. So they observe a very strange trend in their predicted effective temperatures. And what we can see with our results is that we managed to correct this trend. And an important thing that I didn't mention is that in our deep transfer learning approach, we don't use any stellar parameter measurement, any previous stellar parameter measurement, but we indeed use all the available data. We don't use measurements, we just use the spectra for the transference of knowledge. And this was all the part of our work with M Dwarfs. So we will now go to the work that we have been doing more recently with the ultra cool dwarfs. Okay, so our adventure with the ultra cool dwarfs started with this sir, which is Euclid, which is a Greek mathematician, and it is also the name of the new mission from the European Space Agency, that among all other products, scientific products, it will provide an unprecedented wide survey of ultra-cool dwarfs, low-resolution near-infrared spectra. So as we saw that our methodology is applicable on the high-resolution domain, and seeing this unprecedented vast survey that we are going to have, we thought if we could and should use our methodology that we tested in the high resolution with this new spectroscopic survey. But for this, what we need is to adapt our methodology from the high resolution domain to the low resolution domain. And as we don't have still available Euclid data, what we did is to create a testbed environment for the low resolution domain using near-infrared ultra-cool dwarf spectra from the SPEC PRISM library of spectra. Okay. And what we want to do with this testbed environment is just to test if our methodology makes sense in the low resolution domain. So for this, we need a sample of low resolution spectra observed and a grid of synthetic spectra to train the models. For the first one, what we did is to first obtain a good quality sample of ultra-cool dwarfs from the ultra-cool seed, which is the most up-to-date compilation of ultra-cool dwarfs in the literature with spectroscopic classification, with reliable spectroscopic classification. We took this good quality sample of ultra-cool dwarfs and we cross-matched it with the SPECS library to search for low resolution near-infrared spectra. And by doing this, we ended up with 688 spectra that we could use for this analysis. And we didn't take the full spectra, but we only took the wavelength rate that will be provided by Euclid. As what we want to test is if our methodology is of use to the data that will be provided by Euclid. And for the grid of synthetic spectra, what we did is to build a grid using the new Sonora Elf-Volt models. And we enrich our training data set by performing data augmentation, adding different random signal to noise ratios to the synthetic spectrum. So doing this, the first thing that we saw is that in this low resolution domain, the autoencoder is also able to correctly reconstruct the input spectrum, the real spectra. And this is what we can see in these two figures. We have, in the top figure, we have different real spectra, low resolution spectra from SPECS, the bluer, the hotter, the redder, the cooler. And these spectra belong to different stellar types, spectral types, okay? And what we can see in the bottom plot is the actual reconstruction that we obtain thanks to the autoencoder. So we can see that it is not identical, of course, but it is very similar, and more importantly, it managed to get all the important features of the spectra that we will need later for the determination of the effective temperature. And the second thing that we wanted to test and that we saw is that the deep transfer learning step also proves to be meaningful in this low resolution domain. Here you can see the same similar plot as the one I showed before. In blue, you can see a real spectrum, a real low resolution spectrum for L2 dwarf. In red, you can see the reconstruction before the deep transfer learning, and in black, you can see the reconstruction after this transference of knowledge. So you can see how it proves to be meaningful. You can see how the reconstruction after this transference of knowledge is way better. So what we did is to repeat our methodology, the same methodology that I explained for the high resolution domain. We repeated the process using this new sample of data in the low resolution domain. And these are very preliminary results, but what we are finding is that the estimated effective temperatures that we obtain with this methodology have a very good trend, a very good relation with the spectroscopic spectral types that are obtained from the spectral, that are available in the spectral, in the specs database, sorry. So this is what we can see in these two plots, which are very similar between them. In both y-axis, we can see the absolute magnitude in the J-band, as before. In the first figure, we can see the spectroscopic spectral type, and the color of the dots is the effective temperatures that we are estimating with the deep transfer learning methodology. And we can see a very good trend as while the spectroscopic spectral type goes up, so it goes to cooler objects, also our estimated effective temperature is going down, okay? And as you can see, there is a plateau, there is an horizontal line in this relation, which is actually due to the LT transition that I mentioned in the HR diagram at the start of the talk. And we will look into it in the next slide. And our second plot is, we just interchange the predictive temperature with the spectroscopic type, and we can see that the relation between the absolute magnitude in the J-band and the predicted effective temperature that we obtain is much more linear with the temperature than with the spectral type. And we also tested or double-checked our effective temperatures with the same HR diagram that I showed in the introduction. So here in the figure, you have the same HR diagram, the absolute magnitude in J-band y-axis, and the color between the J and H in near infrared bands in the x-axis. Okay, so as you can see, our predicted effective temperatures develop or evolve accordingly to this sequence that we saw at the start of the talk. And you can see how in the LT transition, which is this horizontal line, the effective temperatures remain more or less constant, as is expected, as this had been observed a lot of times in the literature. Okay, and here I included another figure in the other side of the slide, where we can see two real spectra from specs. In the top, in orange, we can see an L6 spectrum, and in the bottom, in red, we can see a T6 spectrum. Okay, and I overplot the J and the H near infrared bands, so you can see how when we transition from the late L, sorry, to the T type, the flux in the H band is strongly reduced, and this is because of the appearance of methane absorption bands. So you can see how the flux is strongly reduced, and because of that, the color J minus H starts to go bluer in this transition. And this is a last plot to summarize the results that we are obtaining in the low resolution domain. Here we can see the relation between the effective temperatures that we obtain and the spectral type that we can find in specs. Okay. So what we can see here is that the relation evolves, like the predicted temperatures decline very steeply for spectral types from M8 to L7. Then we have this plateau where the temperature remains more or less constant in the LT transition from more or less L8 to T1 or T2. And then we have, again, a steep linear relation between our effective temperatures and the spectral type for the T2 and T9 spectral types. Okay, and I didn't say it, sorry, but the dots that you can see with a black, in black with a white edge are the median effective temperatures that we predict for each of the spectroscopic spectral types. And in gray, what you can see is the relation, empirical relation obtained from MAMAJEC for this same relation between effective temperature and spectral type. And you can see how the relation, the median values that we are obtaining evolve very well with a very good trend with this empirical law by MAMAJEC, empirical relation, sorry, by MAMAJEC. And this is just to finish the takeaways that I wanted you to get. The first one is that using a deep transfer learning approach based on autoencoder neural networks, we managed to obtain a new feature space where the synthetic and real data that we use as input for the stellar parameter estimation are much closer. A very important thing, as I said, is that this deep transfer learning process does not involve previous stellar parameter estimations for the knowledge transfer process, because we just use the available spectra. Also, you can find an in-depth discussion of methodology, results, and uncertainty estimations for the M Dwarfs analysis in the paper that was published recently. And to finish, the last takeaway is that the preliminary results that we are obtaining in the adaptation of this methodology to the low resolution domain to study ultracooled dwarf spectra are resulting to be very promising. And this is all from my side. Here you have all my information if you want to connect. So thank you very much.
Fantastic. Thank you very much, Pedro. That was a really interesting talk, and it's fantastic to see how you sort of applying these new methods to sort of stellar parameter determination. It's really interesting. So we've got some time for questions in the room here and questions on Zoom. So if you want to ask Pedro a question, just raise the hand and make yourself known. Miriam.
Hola. Can you say a little bit? Well, I have two questions. One of them is, what's the synthetic gap you wanted to solve? And the second one is where the specs library, what kind of instrumentation was it taken with? Because I'm not very familiar with, I'm not super familiar with infrared observations. And I was intrigued that you don't have telluric lights. So I'm supposing it's something from space or... Anyway.
So first of all, for the synthetic gap, is that we found that the models, the synthetic models that we use to train the models, the deep learning models, sorry, are not identical to the real data that we are inferring to. So the synthetic gap is just the difference in the features between these synthetic spectra and the real observed spectra. So here in the plot, you can see an example. The dashed line is the synthetic one, and the solid line is the real one, and you can see how they are similar but not identical. Okay, like for example, the synthetic data is not doing some of the features, or the depth of the features is not identical to the real data, etc. And
so you are training the network with models.
Yeah, we are training the network with models.
Because again, this is not my field of expertise, but I thought this is not a good idea because you are kind of predetermining the network and how to think.
Yeah.
So
that's why
there are some people that have a very strong opinion against this. So
yeah, so that's what we add the deep transfer learning model, like the deep transfer step, to try to make the observed data closer to the models. And for the
But again, it's trained with the models.
Yeah.
Even
trained
though
with
it's
the models.
different
Yeah.
models that work for another situation, but
Yeah, it's trained with the models and tailored to the real data.
okay, thank you.
And for the specs, it's a spectrograph from Earth. From Earth.
And how do you remove the telluric lines?
That you can see. Yeah, sure.
Because here you have J band and H band. So somewhere in between you have pieces where the atmosphere fully blocks the light. So or maybe this is just a library and somebody else takes care of this, but it would be not good to know how they do it.
These are I don't know, like the calibration processes, but I can look into it.
Okay, thank you.
Thank you.
Yeah, if I may, I can help. This is Maria Rosa speaking.
Yeah, Rosa, we can
Okay.
just about hear you in the auditorium, but I think we can turn you up a little bit so you can comment.
Yes, it's to provide an answer to Miriam's concern. And the tellurics are removed using stars, hot stars that are observed immediately after the targets. So, of course, there are some errors due to telluric correction, but telluric correction is done in this way.
Thank you, Maria.
Thank you, Pedro.
Yeah, there is another question on Zoom by Diego. You can unmute yourself and ask the question, Diego.
Thank you. Can you hear me?
Yes.
Okay, perfect. Well, first of all, thank you for the talk, Pedro. It's been very interesting. I've noticed that when you were comparing the results you obtained for the stellar parameters with previous studies, in those plots, the error bars, how are they obtained? I mean, how do you estimate uncertainties for these stellar parameters with your methodology?
Okay, thank you for the question, Diego. So in our work and in theirs, what we do to obtain these uncertainties is to actually repeat all the methodology that I talked about using different architectures. So first we do a very extensive grid search for the optimal hyperparameter combinations for the autoencoder networks. And with that, we obtain several architectures that are obtaining the best results. Okay, so what we do is to take a lot of different autoencoder architectures, and then for each of these architectures, we do the parameter estimation process with the convolutional neural network. We repeat it several times. So with this, what we end up is with a distribution with a distribution for the stellar parameter estimation for each one of the stars. And once we have this distribution for the stellar parameter, we approximate it with a kernel density estimation, and we take as final value the max of this kernel density estimation, and as uncertainties with the 1 sigma quantiles, like the Q16 and the Q68. And this is a method. This is how they have been doing it, like in the last 2 previous papers. So we just did it like this for to have a similar comparison with the results.
So it's, if I've understood well, different configurations, but with the same with the optimal hyperparameters, right?
Can you repeat, please?
If I've understood well, you find the optimum hyperparameters, this is fixed, but you use different configurations with the same hyperparameters. Is that right?
Yeah, we use the same architecture, but with different combinations of hyperparameters. that
okay.
we found out that obtain very good results.
Okay. Thank you.
Okay. Thank you.
Microphone problems there, but yeah, so do you have plans to go beyond just estimating iron abundance? So because I would have thought with the sort of, at least the CARMENES spectra that you are showing, that it would be possible to determine individual abundances for different elements.
For the low resolution spectra, we are testing this, but we are not obtaining good results because they are not capable to estimate this. But maybe in the future, we can develop some kind of methodology that is able to do it, but not at the moment.
And the high resolution stuff?
And the high resolution stuff, we can do it. Actually, there are a lot of work within the CARMENES consortium for these abundances, but we just stop like in these stellar parameters.
Just as a kind of first.
Yeah, we estimate each of the stellar parameters independently.
Yeah.
Not at the same time.
Okay.
But there is a lot of work for abundances with machine learning, so maybe you can.
Yeah, it looks really interesting. So, any further questions for Pedro in the room or on Zoom?
No, on Zoom we only have José Luis Graguera that says preciosa presentación.
Thank you, José Luis.
And I'll just give a final opportunity for anyone to ask any further questions. And if not, then we can thank Pedro again for a fantastic seminar. Thank you, Pedro.
Thank you.